So welcome back, everybody. The aim today is to discuss this topic of importance sampling, but we need to go a little bit back and forth between the lectures from last week, where we looked at the derivation of the Metropolis Hastings algorithm, and then link this with the topic of importance sampling. And we're going to look at some practical aspects, but there are also several technicalities which I wanted to remind you of. And then finally, there is a link to equations from transport theory, which we will cover in a more hasty way. And these are the so-called Fokker-Planck and Langevin equations. So if somebody here has studied statistical mechanics, perhaps with a small sprinkle of transport theory, then you may have encountered equations like the Fokker-Planck and Langevin equations. To give you the overarching argument here, so importance sampling, which is widely used in Monte Carlo samplings, is simply used to guide the random walkers in a more efficient way, so that the random walker is going to follow the physical distribution of the system. The examples which we went through last week and the week before, they contained what we normally call a brute force implementation of Monte Carlo sampling, which means that we accept the given step with a kind of 50% likelihood. So it's a kind of tossing the coin. So we suggest a move, and then we try to fine-tune these moves so that roughly 50% of the moves are accepted. If you accept all moves, that means often that you just stay in one place. So you barely move and you don't sample the whole distribution. So importance sampling is a way to guide your random walkers according to the distribution which you have chosen. And it's a technique which is widely used in Monte Carlo calculations. Whether you're calculating an integral, a stochastic evaluation of an integral, or if you're doing statistical mechanics and want to let the random walkers jump in space in a more efficient way, following the distribution, so that when you jump into regions where the distribution is non-zero. So the things which I wanted to say a little bit about is the topic which are going to come now. So the plans for this week is first to give a kind of overarching view, but I'm going to go back a little bit to what we did last week and remind you of some of the basics of the Metropolis Hastings algorithm. And then from a technical point of view, since we now are going to implement importance sampling, it means that we're going to need the gradient of the probability distribution. And this kind of gradient is often called loosely a quantum force. And this is something which we need to implement computationally. And finally, and this is something which we will probably cover next week, is that we will try to link this with the Fokker-Planck and Langevin equations, which are ways by which we will implement importance sampling. So there is a lot of disconnected things, seemingly, which I will try to bring together here. But let me switch to the whiteboard now, and then remind ourselves a little bit about what we did last week. So what we have are three key ingredients in all these calculations. So one is importance sampling, and then we have the Monte Carlo Markov chain, and then we have the Metropolis Hastings algorithm. So these are the three most important ingredients which we are going to deal with. And if we now want to summarize a little bit of the discussion from last week where we derived the Metropolis algorithm, so what we have is what we normally call a detailed balance from the Metropolis algorithm. When we derived the Metropolis algorithm, and this follows from the theory of Markov chains. And I'm going to quickly repeat what a Markov chain is. So I hope you don't get offended if I repeat some of the material from last week. And then, so we have a Markov chain with a probability. So let's just now be generic. So we have a probability of being in a specific state, which we can label as a Wi of t. So I is a specific state, and t is a probability of being in that specific state at a time t, or after you've been stepping around in this configuration space a given number of steps. So you can think of this as time. There is also a probability or transition probability. Now, these probabilities, they obviously behave like probabilities. So if I sum over all the values I, this is normalized to 1. And then we have what is normally called a transition probability. And we can think of that in a loose way as us making a transition from a state j to a state I. And this is normally rewritten in terms of a matrix element, Wij. And this is also a matrix which is a so-called stochastic matrix. And what we have is, so this is normalized so that Wij, when we sum over all the columns of that matrix, this is now normalized to 1. And a typical example of such a matrix is a matrix which we saw last week. So let me just quickly remind you of that. So we could have a matrix which looks like this, just to give you an example. 1 divided by 4, 2 divided by 4, 0, 1 divided by 4. And then we have 1 divided by 9. These are just numbers which I made up on the fly. And 5 divided by 9. And then we have 3. So these are probabilities of making a specific transition. And you see now that all the columns here, they sum to 1. And this is an example of a stochastic matrix. And a stochastic matrix has also the property that its largest eigenvalue, so lambda max of this matrix W, is equal to 1. And when we set up a Monte Carlo Markov chain process, or a Markov chain process, what we typically are looking after is a transition from a specific state, I, to a new state. So we would end up in a state I of t is now given by this probability distribution, this matrix W, where we now just write this in a looser way, j to I. And this is now multiplied with the probability of being in the state j at the previous time step delta t. So we are going to, when we use a Markov chain, this is essentially the theory for Markov chains, which is written here. So you have a stochastic matrix, which represents a transition probability from a given state to another state. And it's assumed to be time independent, normally. Assumed time independent. And if we rewrite this in terms of vectors times matrices, so when I drop the subscript I and j, you should read these as vectors. We can rewrite this one as a matrix W multiplied with these probabilities at a time t minus delta t. Now, we say that this Markov chain process is independent of previous probabilities, so it depends only on the step before. And all the history before that is normally forgotten. And the example which we had in the slides from last week is if you take now a vector, an initial vector, you could now assume that this Wi at t equals 0, the state we start with, is given by 1, 0, 0, 0. This could just be an example. And then we can apply this matrix a given number of times. And if we perform this operation here a large set of times, so in this case, it converges after 13 time steps, but we are just going to write infinity here. Then this converges when we apply this matrix. This converges to the following values with this number of decimals as leading decimals here. 0.057, and then finally we have a 0.37900 here. So obviously, if you want to add more numbers, you would need more iterations than 13, but it roughly converges to this final state here. And this is the state which also corresponds to the largest eigenvalue, which is equal to 1. And this represents what we normally call the steady state. So the theory of Markov chains is a theory which is used to derive the Metropolis algorithm. And what we would typically have is that in the limit, if this converges, the limit t goes to infinity, then what we have is that we have the state wt is now given by w of omega of t minus 1. So I'm just, instead of writing minus delta t, I just write minus 1. And what we are going to have at the end is w of t equal infinity is equal to this matrix, which is assumed to be time independent, and multiplied with the solution at time equal to infinity. And we can actually see that if we now think of this specific process as a wt, if we now want to understand a little bit better what is going on. So we can apply this matrix t times to the state at t equal to 0. Now, what we could do now is to expand this vector at time t equals 0 in terms of the eigenvectors of the matrix W. So we can actually rewrite this now in terms of a set of eigenvectors, V of I, and where V of I are the eigenvectors of this matrix W. So we had a set of eigenvalues and eigenvectors of this specific matrix. So if we now apply this matrix to this states, t times, you see now that what we end up with, if we now look at t equal to 1, which is simply now wt applied once to this state of t equals 0, that is the same as us applying this matrix on w of alpha I multiplied with this v of I. And this is nothing but lambda I, alpha I, which is just coefficients, which we can assume that are known. And if you apply this t times, what happens then is that wt is equal to w of t multiplied with the initial state, which we prepare the system in. And this is going to be equal to a lambda of I, t times, multiplied with this coefficient alpha I of v of I. And typically these eigenvalues could now be organized as an ascending or descending series. So the largest eigenvalue is equal to 1. And then this is assumed to be larger equal than lambda 1, larger equal than lambda 2, and larger and equal to the final eigenvalue of lambda n minus 1, if this is a matrix of dimensionality n times n. So that means that this state wt is now going to be proportional with lambda 0 of t, which is the largest eigenvalue, times alpha 0 of v0, plus the remaining states, where these eigenvectors are these eigenvalues are normally smaller. So we would sum from I equals 0. And in principle, we have an infinity of such states if this transition probability is infinitely large. So that means that we end up with an alpha of I, of v of I, and then we have a lambda of I of t. And then we can obviously hope then that in the limit, where t goes to infinity, then we have that this vector wt, which is now a probability, is equal to lambda 0 of alpha 0 of v0, and that we can neglect all the other contributions. And this lambda 0, which is the largest eigenvalue of the stochastic matrix, is equal to 1. So this is a definition of a stochastic matrix. In our case, what we have is a probability wi of t, which now is given by the quantum mechanical probability. So we would have something like a P, and this depends on a specific state, obviously, of the system. But let's now write this in a more generic way. So it's going to be a function of all the collective quantum numbers of the specific system we are looking at. And then we have this vector which contains all the variational parameters, which we are going to vary. And this is typically given in terms of a trial wave function, where we put this T, and then we have this R, which now contains positions and additional quantum numbers. So we can just think of that as a generic container for all the quantum numbers which are needed to specify that specific system. And then we had an integral, a multidimensional one, over the trial wave function. So this is the kind of probability distribution which we are going to look at. And what we end up with then, what we discussed last time, is the Metropolis-Hastings algorithm. And in the discussions of the Metropolis-Hastings algorithm, so let me just quickly remind you a little bit of that, because that's the algorithm which we are going to use in order to accept a suggested move or reject it. So the Metropolis-Hastings algorithm starts with the Markov chain. And in general, this transition probability, not a vector sign here, sorry, which we wrote as a Wij, this is unknown, and it is represented by a multidimensional object. If you're thinking of a quantum mechanical system which makes a transition to a new state under the influence of some external probe, this kind of transition probability is in general represented by a multidimensional quantity, and it can be almost impossible to simulate from that. Actually, even your probability distribution, which you have here, is a multidimensional object. And you see also that calculating the normalization factor here can actually be a pretty difficult topic. And the Metropolis algorithm saves the day in a sense, because we're taking ratios between probabilities. And this probability distribution here is normally unknown. Is normally unknown. And that means that we are free to model this as we want. And one of the standard approaches which is normally used is that this transition probability, and now I'm just going to keep this loose notation with J going to I, is now split into a probability of J going to I. And then we have a new probability, which we call for the acceptance probability. I have a tendency to put these arrows on top of the letters. So this is the probability of making a transition. So it's not the same as the W, which is a total probability of making the transition. So this is probability of making a transition. And in some cases, if you're looking at a single particle problem, if you think of the hydrogen atom, you can actually calculate the transition probability due to electromagnetic processes from one excited state to the ground state. This is one of the few cases where we can actually get analytical expressions for this probability distribution. So probability of making a transition. This is another probability, and this is the probability of accepting a move. Of accepting a suggested move. So as I said, this object which we have, this transition probability, which if we look at this in a discretized way, it can be an infinitely dimensional matrix. This is normally an object which we do not have knowledge of. The example which I showed you up here is just an example which I made up, just to illustrate what are the properties of a stochastic matrix. So if you take this matrix here, you see now this is normalized, all the column vectors are summed to 1. You can change column vectors to rows, they should be normalized to 1. And this matrix has the largest eigenvalue equal to 1, which is one of the definitions of a stochastic matrix. And the thing is that we, in general, we don't know what this looks like. And the Metropolis algorithm is the algorithm which comes to our rescue here. So in our case, this probability which we have is given by the little w. And if we now look at the Metropolis algorithm, which we went through last time, what we end up with is what is normally called the Metropolis-Hastings ratio based on detail balance. So the Metropolis-Hastings ratio. And this is given by the probability of being in a state I. And now I'm dropping this time. So I'm just looking at the probabilities of being in a specific state. And this is given by these probabilities of making this transition from J to I, multiplied with the acceptance of J to I. And this is divided by T of I to J. And then we have this acceptance probability of I to J. Now, in many cases, you don't know this probability T. And this probability T is something which we are going to make a model of now. So let's just wring it out. So this probability T, this is normally unknown. Now, in the simple Monte Carlo metropolis, or just metropolis, what we assume then, when we take away Hastings, so the simplest implementation is to assume that this is a reversible probability. So that means that going from J to I is given by the same probability as going from I to J. So for those of you who have taken a course like Computational Physics 1, where you've looked at the Ising model, when you have this kind of spin systems, this is one of the cases when moving from one position where you flip a spin and then going back again, this is normally assumed to have an equal probability for flipping the spins. And then we would say that this spin flipping probability is a reversible probability. Now, when we're now going to jump in space here, this may not be the case. So the whole thing with importance sampling is actually to find a mathematical expression for this probability distribution. So the standard Metropolis algorithm, when we take it as it stands, what that means, so the standard which we have seen before, in our explicit case, is that this Wi of Wj here, that translates into the following. So it's a ratio between probabilities of the trial wave function. And it's going to be given by the particles in a specific position and with a given set of variational parameters divided by this psi of t of rj, the previous position. So note as well that in this first project, we are not going to flip the spins of the particles. That means that we do actually have a system which has zero spin or an even spin. And spin is a degree of freedom which we are not going to be concerned with. If you're dealing with fermions, on the other hand, and your Hamiltonian depends on the spin degrees of freedom, what you would need then, you would need to have an algorithm where you also flip the spins when you move an object. Now, when you think of moving, and this is something which is important to keep in mind, so you can think of moving collectively all the particles and then perform the test. Or alternatively, and this is something which you will see from the mathematics, it is actually more convenient from a computational point of view to flip one particle at a time, because that's going to simplify the ratio of the for the Metropolis test, but also it's going to simplify the calculations of the local energy. So there are two considerations which I want to bring up, but before we do that, let's now just bring back the simplest metropolis algorithm. So this is going to be equal when we now assume that the transition probabilities are reversible. Then it's just going to be a function of the acceptance probabilities, where we now have this j to I divided by a of I going to j here. So that's the simple brute force standard metropolis algorithm, where we don't impose any kind of constraints on a probability for making the transition. And the algorithm translates into, since these acceptance probabilities are also probabilities, so that means that they take values between 0 and 1. We are assuming that they are normalized. And what we typically assume then is that if the probability of going to a new state is larger, then what we give is that we give to this acceptance probability the maximum value. And we assume then, obviously, if this ratio, which is, so this is one of the basics of the metropolis algorithm, which simplifies the calculations. If this is larger and equal to 1, that means that we go to a region with a higher likelihood. And then what happens then is that we put this A of I, this is actually J, going to I. So I hope you can see the distinction between my J's and I's. We put that one to the maximum value. You can have other sampling rules. That's possible, but this has been demonstrated to be the most efficient one. Then, if you take the other approach, if Wi of Wj is less than 1, but larger than 0, so clearly we also have larger than 0 or equal to 0, then what that means is that we put the reverse probability of I going to j equal to the maximum value. And then we simply pick this A of j going to I to be given by a random number between 0 and 1. So this becomes equal to a random number between 0 and 1 here. So that means that we would typically compare these ratios of probabilities with a random number. And if that ratio is smaller than than 1, then we just assign a random value to this Aij here. So this is basically the metropolis algorithm for making the transition. And this is normally rephrased in terms of the following. So we would have this probability of going from j to I, which is given, I don't know why I have this bad habit of putting an arrow instead of putting a dot on the letter J. I don't know why. This must be a tick I have developed this morning here. So this is now given by the minimum value of Wi divided by Wj, these probabilities, and 1. Now, the thing is that this normally leads to sometimes a very inefficient algorithm. So the typical way we also implement this is to have, if this a random number R, where R is a random number now between 0 and 1. If this is smaller or equal than this Wi, actually smaller than Wi and J, then we assume that the test is accepted. Then we have a new position, which we just labeled with RI is accepted. And then we would update expectation values, and we will also update the wave function. So we would now calculate the local energy. We would also calculate the contribution to the local energy squared in order to be able to calculate the variance and other statistical properties. And then else, if this is not the case, then we will simply set the new position to the old one. And we would also update the variables here. And then we would simply add to the averages. So we will also count not moving as an observation. So not moving is counted also as an observation. So let's just emphasize that. Not moving is also a measurement. And then we keep accumulating this till we have run through all the Monte Carlo cycles which we have pre-established. Now, if we now take the Metropolis-Hastings algorithm, if we modify the above, so let's just finalize everything. So what we would have then is that this ratio changes now. So this acceptance ratio of making the move from J to I is now given by the minimum. And now we have the probability Wi of Ti going to J, and then divided by Wj of T of J to I. And then we have 1 here. So this is the type of calculations which we need to implement. Now, the thing which becomes important for us now is actually to think of a model for this Ti going to J. So we need a model for Ti going to J and vice versa, unless we assume that these are reversible probabilities. And in that case, Ti going to J and Tj going to I, they are just equal, and then they disappear from the factor which we have to evaluate. So the basics of the Metropolis algorithm are contained in these simple equations. So we are assuming that in case you move to a higher probability, we accept that move without contesting it. If we are moving to a lower probability, what we are saying now is that we accept this move with a certain constraint. And that constraint is implemented by a random number between 0 and 1. So if the ratio is small or equal to a specific random number, then we accept it. If not, we would continue with staying in the same position and suggesting new moves. So this is the some of the basics of the Metropolis algorithm, which we also covered last time. And you can see that graphically, if you now think of a probability distribution in one dimension. So if you think of a Gaussian, or actually a normal distribution in this case. So we have a normal distribution with 0 mean value and a specific value of sigma squared. And if we plot that one in just one dimension, so we have x, and then we have minus x here, and then we have 0. So this probability distribution looks something like this. And you can see my drawing skills haven't improved with age. So, but assume this looks like a symmetric normal distribution here. So clearly, if you now, so this is the distribution, P, which is proportional to this normal distribution. And it has obviously its maximum value here. So if you select randomly a position x0 here, you can suggest a new move. So you could now think of x1, which is x0 plus some random number times a step size. And since we want to move between minus infinity and plus infinity, we have to be a little bit careful with the way we design this, because this r is normally a number between 0 and 1, so we would draw this randomly. And having drawn this randomly means that what we have then is a number which is just between 0 and 1, but we can change this one by simply rewriting it in terms of this R0 minus 0.5. So we could actually rewrite this more like x0, x1 plus this number R minus 0.5 multiplied with this parameter delta. So delta is a parameter which we choose. So delta is a chosen parameter. And this is a parameter we can tune So we can use this kind of ad hoc rule where we say that we want to have a random walk process where we accept roughly 50% of the suggested moves. So this is nothing but a kind of tossing the coin approach, because we don't have an intelligent way by which we can guide the random walker. And that's why this is also often called just a brute force Monte Carlo sampling. It's from a computational point of view, it gives you less cycles because you don't inform the random walker about the probability and how the random walker should jump. However, it gives you an algorithm which normally has less accepted steps, and you have to fine tune this parameter delta. And you can see here now that since R goes from 0 to 1, then clearly we would have, if R is larger than 0.5, we get a positive number. If it's smaller than 0.5, we get a negative number. So suppose now that this x1, where we are here now, we jump to x1 here. And then clearly this is a region with a larger probability, so that W1 divided by W0 is larger than 1. So we would accept that suggested move flatly without contesting it. Then we can continue like that. So if we only accept those kind of moves, suppose now that x2 is here, then we are moving to another high probability, and we know that W2 divided by W1 is larger than 1. Now, if we just accept those kind of moves, at the end, we will just be here. So if you run this, let's say 1 million times, so you allow for 1 million random walks in space, what will happen then, suppose now that you, after 3 moves, so when you have x3, you're here. And you're performing 1 million Monte Carlo cycles. It means that out of this 1 million, there will only be 3 which samples this region here. And the rest of the 1 million minus 3 Monte Carlo samples will just give you a contribution to an integral where you are here. And that will give you an extremely biased contribution to the integral and very poor results. So that means that we need to have the possibility where we can now jump from x3 back to this region. So this could now be our x4. And now you see that x4 gives a probability which is less than 1. And then we are going to accept this probability with a certain likelihood, which we then rephrase in terms of this random number. So that means that we need those probabilities, so that at the end, we would now be jumping back and forth in this space of possible probabilities. And then at the end, all these kind of positions here are going to make up the contributions to a specific integral or to a quantity we're going to calculate. So I just wanted to remind you of some of the basics of the Metropolis algorithm, which we went through last time in this pre-recorded video, just to remind you of the motivation for what is coming now. So this algorithm, which we have looked at now, where we assume that the transition probabilities are reversible. So that means that when we look at the ratios here, the ratios between these two guys just gives 1. Then in that case, this translates into a very simple algorithm where we just suggest moves with a parameter delta. And if we make that parameter too large, we will be jumping in and out of regions where the probability is 0. And if we tune it properly, we will always stay within regions where the probability is non-zero. Because remember now that if we have this probability, when we calculate a given observable, if we're now thinking of this in terms of an integral, where this x is given by a specific domain, this is given by this integral, and if we have a continuous variable, what we are going to do is actually to replace this with a given number of Monte Carlo cycles n, and this is going to run through the suggested moves. And then we are going to simply compute these different values of x. This is essentially what we do. So clearly, if we can optimize this move in the space where this probability distribution is non-zero, that will obviously save us a lot of cycles, and we won't waste cycles in regions where the probability distribution is 0. So if you look at this integral here, clearly, if I'm sampling lots of points here, I'm going to have 0 contribution. And we don't want that. So the way we tune this parameter is something which becomes a little bit ad hoc. And what we want now is to move away from delta to what is called importance sampling. And after the break, I wanted to give you some of the basic equations and show you how we can implement them. And then next time, we are going a little bit back to the theory and try to link the dots between the way we are going to simulate this importance sampling and how we are going to implement it. So today we will also discuss how to implement it, because that means that we get an additional quantity which we have to look at in the calculations here. Okay, we are going to take a small break. Feel free to ask questions. In the meantime, I'm going to put the recording on. So if we now look at the equations which we reminded ourselves about, the problem which we have, if we want to use the Metropolis-Hastings algorithm, is that we do need a model for this transition probability. So as I said before the break, I mean, this is the probability for making a transition, but it's not the total probability of making the movement to a new position, because we have split that total probability in terms of the probability of making the transition and the probability of accepting that transition. So the Metropolis algorithm, the way it was designed originally, was just in terms of acceptance probabilities, which makes it pretty simple to simulate the system. The Metropolis algorithm has also been proven to be so-called ergodic, which means that if you are able to simulate all possible paths which a random walker can take in space, if you have an infinity of time, then the algorithm should allow you to traverse all possible paths. On the other hand, if you have a biased algorithm, it means that it would only select some specific paths. And that means that your sampling will not be ergodic, with consequences like a biased final result. So the Metropolis algorithm belongs to these classes of algorithms which obeys the ergodic principle, which is actually very difficult to prove, by the way. And the other quantity which we looked at, or the other mathematical detail, was that of detail balance, which ensures that the random walker, or the stepping which we do for a Markov chain process, allows us to reach the steady state. And in case that doesn't happen, we may have something which is called a circular solution, where we can be in one state for some time, and then we can move to another one, and then to another one. In principle, what we want at the very end is that our system reaches what we call the steady state, and that corresponds to the state with the largest eigenvalue of the stochastic matrix. However, these are quantities which we are not able to quantify properly in our calculations, because we do not have a specific model for the transition probability. Like in the case in the beginning of the lecture, we assume that this transition probability could be modeled by this stochastic matrix. In principle, this stochastic matrix is infinitely dimensional. We don't know it. And that's where the Metropolis algorithm comes to our rescue, because we can simulate systems without knowing that transition probability, because at the end, we are calculating ratios between probabilities, and that's the magic of the Metropolis algorithm. So the Metropolis algorithm simply deals with this ratio here. And that's something we can quantify if we have a model for the probability distribution, Wi. Now, there's one thing I also wanted to add, and which we're going to repeat a little bit as a kind of technicality. The way we move our system or suggest new moves is something which we have to keep an eye on from a computational point of view. So we could obviously move all particles and then perform the metropolis test. But if we move all particles, you should keep in mind that this object which we have, this Wi, is in principle a multidimensional object. And even if we have an expression for it, it can be costly computationally to simulate from it. And that's why in specific cases, like when we are dealing with the trial wave functions, which are the products of single particle wave functions, then it is ideal to actually move one particle at a time and perform the metropolis test. And you will quickly see why. We are going to address this again and again. So when you do the metropolis sampling and you perform the test, you can obviously move all particles and perform the test, or you can move one particle at a time. And computationally, we are going to see that for both fermions and bosons, this is going to be advantageous from a computational point of view, because the ratios between the wave functions reduces just to ratios between single particle wave functions. And they are at most three-dimensional, if we are in 3 dimensions. So that's one of the considerations which we need to take. Now, one of the things I wanted to bring up now, since we now need a model for this transition probability. So we need, as we just said before the break, we need a model for this T of I to J here. So the not knowing this probability distribution means that we can make some attempts to link it with the things which are known. And one of the standard links is actually to link this with diffusion. Now, I know that most of you have not taken a course in transport theory. You may not have taken an advanced course in statistical mechanics. So if you look at diffusion theory, the process of diffusion is intimately linked with the Markov chains. You can actually derive the diffusion equation from a Markov chain. If you go back into my lecture notes in computational physics, there is actually a derivation of the diffusion equation starting from a Markov chain. So Markov chains are processes which are intimately linked with diffusion. And then it is tempting to start with a model for this transition probability given by the physics of diffusion. So let's try to look at that and see what kind of probability distribution can come up. So suppose now that we look at the discretized case first. And in this discretized case, what we are assuming is that the system is in a state I at time 0. So this is time 0, time t0, which I just set to 0 for convenience. And let us assume now that this is just given by a delta distribution, delta I, and then I'm having time 0 here. Since this is a discretized distribution, a discretized case, this is just a Kronecker delta. And I have a Wi of t at a new time step, which is now the sum over all the probabilities which I have, the states it can be in, j to I, multiplied with this wj of 0, which we have assumed to be a very, very simple choice here. Now we can move to the continuous choice, and then this function translates into a delta function. So we are going to let wi of 0 go over to some w of x, and I put a tilde here, and at time t equals 0. And this is going to, no, sorry, x, not tilde, but x vector. So it's in, can be in more than one dimension. And this is going to be given by the Kronecker, no, the delta function. So you can think of this as something which is sharply peaked. Now, there is a continuous variant of the Markov chain. So we've looked only at the discretized Markov chain, but the equivalent continuous Markov chain is now given by us being in a state y. This is the new state at a time t plus delta t. And that's given by an integral over all the possible positions or events which the system can be in. And then we have a transition probability where we move from x to y in a time step delta t. So in this specific case, we're assuming that there is a time dependence, but normally we will take away that time dependence, delta t, and this is multiplied with the probability of being in this position x at a time t. So when equilibrium has been reached, in equilibrium, there is no time dependence anymore. So this is the steady state. So the equilibrium variant here is given by W being in a state y, which is given by an integral. And then we have a W and we take away time. So we assume that this transition probability is time independent. And then we have a dx at the end here. It should also be multiplied with dx here. So we can now find this probability distribution by what's normally called a Fourier transform to k-space. So if you look at this equation here, what we would like to have now, we can Fourier transform to k-space. This is a standard technique which is used. And then we can express this quantity x as a function of t before equilibrium has been reached. And when we have an integral from minus infinity to plus infinity, we have an exponential of I k x. And this is multiplied with the same probability with k and t and an integral over dk here. We also know that the delta function, which we had in the beginning, this delta of x, it can be represented in terms of an integral. And this is given by the exponential of I k of x of dk. You may have seen these equations. If not, I'm just going to list them here for the sake of completeness. And then we have this probability at k at time equals 0, which is simply now 2 over pi, if we use the definitions which we have for the delta function. And then we can look at the Fourier transform diffusion equation. So we take a Fourier transform, that's a standard way of solving partial differential equations, but performing a Fourier transform for the diffusion equation. Diffusion. And in that case, what we have is so this is the probability of x of t. If you look at this equation here, this is a dt. This is now given by a diffusion constant, and then they have the spatial derivatives, the second derivative, which is something which is proportional to kinetic energy. And then we look at the k-space variant of that one. So we have this new probability distribution k of t over dt, and that's going to be given by a minus d, and I'm going to have a k squared, and I'm going to have the probability distribution here. And this is something which we can solve. We know the solution of that one. This is easy to solve. That's why people often use Fourier transforms for solving differential equations. And we can easily find the solution here for k as a function of t, and that's given by a w of k at t0. And this is multiplied with the exponential of minus d of k squared of t. And this is equal to 1 over 2 pi, and then the exponential of minus d, the diffusion constant, k squared times t. And then we can plug that back again into the equation for x. So we would now have a Wx of t, which then is simply this integral. So we would have then an integral from minus infinity to plus infinity. And then I have the exponential of I kx multiplied with the distribution in the momentum space. So what you're seeing here is just a standard technique which is used for solving these differential equations and multiplied with dk. And this is something which has an analytical solution, and we can actually write it as a 1/4 of pi of dt. And this is given by the exponential and minus x squared of 4 dt. So what that means is that we can actually plug in the probability distribution in the diffusion equation and then find the probability distribution, an analytical expression for the probability distribution by solving the diffusion equation, since we know that Markov chains are intimately linked with the physical process of diffusion. So what we can show, that if we now look at the transition probability, so the uppercase letter of y of x as a function of a delta t here, we can plug that one into the diffusion equation. This is a slightly more complicated integral, but it's doable. This can be found to be given by 4 pi d, the diffusion constant, times this time step delta t, multiplied with the exponential. So I'm just listing these things because there are some derivations here which are not that exciting, such as calculus of integrals. And I'm just listing the final result to motivate what is going to come here. So we could actually make a model for this transition probability. So that means that what we could say now is that this transition probability j to I is now given in this time step, is now given by this probability of making the move from x to y in a time step delta t. And this probability distribution is now given by the quantity which we see here. So this would be the solution of the diffusion equation as it stands with only the diffusion term. So this is solution either for the transition probability or the diffusion equation, for this probability distribution Wj goes to I, which in our case is now given by us moving from a position x to a position y of delta time step delta t, and that's the same as this quantity which we defined as x, y, and t in its time step delta t here. So if you now look at this, what we want to in the Metropolis-Hastings ratio, so this could actually be one way of doing that, because we have a model for now this transition probability based on diffusion, and we could now think the random walker jumping from a position x to a position y with this probability. So what we could do now is that to modify the Metropolis-Hastings, or to actually put in a model for the transition probability, so that we would actually have a w, and now we're going to say that we are in a position y, starting with a position x. So this is our wi and wj's as we discussed before. And this is now going to be given by the acceptance probability of moving from x to y and multiplied with this probability of y, x, delta t, and divided by the acceptance probability of moving from y to x, multiplied with the probability of the transition probability of going from x to y. So this is the case where we actually solve the plane diffusion equation. Now, if you look at this equation here, and if you look carefully at this term here, and then you go back to the expression for the term, which is given by this equation here. So we can actually solve the diffusion equation analytically for these type of distributions. So if you have a distribution which is a Gaussian, you can actually show that. Now, if you want to implement this specific solution to the diffusion equation, what happens with the ratios of the transition probabilities? So if we single out this, what can you say about this ratio here if you use this probability distribution? So feel free to unmute yourself or just write it in the chat. It's going to be equal to a very simple number if you use that specific distribution.
The ratio is 1, both are the same because the
exactly
W is.
So this is, if we use this, so we were inspired by the fact that the Markov chain links with the diffusion equation. And being inspired by that, we know that there is a solution to the transition probabilities when you start with a Markov chain, the discretized Markov chain, which we had here. So this process, so these are actually, I hope you can accept the overarching view of things, because if you want to see the whole derivation of, let's say, these quantities here, that would take us a series of lectures. There is a textbook which I refer to, which contains all these mathematical details. And that's this textbook by Van Kampen, which is called Stochastic Processes in Physics and Chemistry. I'm coming back to that when we look at the slides. So the whole theory here is based on these elements from Markov chains and stochastic processes and the theory of the physical theory of diffusion. So if we use this, the problem, as was said here, is that in this specific case, what we end up with is that we cannot use this relation actually, because it doesn't give us anything new, since the ratio is just equal to 1. So we need something different. And there is a modification to this. So if you go into the transport theory, this is something which is called the Fokker-Planck equation. So I'm going to motivate, what I wanted to do now is to motivate the equations which we are going to program. So the Fokker-Planck equation is the diffusion equation, but in addition to the diffusion equation, there is a term which accounts for the particle moving in a specific field. So if you think of the diffusion equation, you have a probability P of X. Let's just keep this in one dimension. So P is a probability like our W of T is given by some diffusion constant. And then I have the second derivative with respect to X, since we're just in one dimension now, of dx. This term here plays the role of some kinetic energy term or kinetic term. But you can add to the diffusion equation a complication. And this complication arises due to the particle, for instance, moving in an external field. So that gives us a drift term. So the Fokker-Planck equation has the standard diffusion term plus a drift term. And it's actually the implementation of this drift term which now is going to give us this probability distribution. So this term here is now going to give us a modified transition probability. Now, there is a reason for why people use the Fokker-Planck equation. And that is, for some of these systems, we can actually solve the Fokker-Planck equation analytically. So we are going to get an analytic expression for this probability transition, or this transition probability. So I want to have you with me on this kind of more overarching arguments. So we have the Markov chain, which links intimately with diffusion. Now, from diffusion theory, we can try to extract a transition probability. So this quantity which you see here is indeed a transition probability. And if we just keep the standard diffusion term only, we can solve that analytically for this quantity here. But we can also solve it analytically for some specific drift terms. And that's what's going to allow us to find a model for this transition probability. So this is going to give model for this W, which we just loosely call from J to I here. And the benefit when we are writing a Monte Carlo code is that we now can guide the random walkers according to a distribution. And you will now see that this distribution is going to be closely linked with the probability distribution which we have from quantum mechanics. So in our case, this Wj of I will be linked with a quantum mechanical distribution which we are studying, with this distribution which we have, this psi of t of Ri of a set of parameters alpha, the variational parameters alpha. So this is something which we're now going to look at in a more superficial way, and then hopefully next week we are going to link some of these topics with the theory of diffusion, with the Fokker-Planck equation, and another equation which we are going to need, which is called the Langevin equation. So these are intermediate steps which we need in order to implement importance sampling. This is one of the ways of doing that. There are other ways as well. And many people actually now, in order to save CPU cycles and not complicate the calculations, they drop importance sampling and they pay more emphasis to the optimization part of the parameters. And that means that elements like stochastic gradient descent, which we're going to encounter, something which is called stochastic reconfiguration, and other techniques, which we will also discuss a little bit later, often used instead of adding this complexity of importance sampling, because it steals CPU cycles. But in our case, we're going to implement it, and that means that we don't need to use this kind of ad hoc rule. There will still be parameters we need to plug in, but these parameters are motivated from the theory of diffusion and Markov chains. So what I want to do now is actually go back to the slides a little bit and show you the basic ingredients which we need to have in the code. So let's just bring up this. So the thing which I wanted to briefly argue for, and the slides here also contain the background material. So I mentioned to you that there is an excellent textbook by Van Kampen, and there's also a textbook by Gardiner, which I think you can download it for free, which also deals with stochastic methods in the natural sciences. There's also a nice lecture on the Langevin and Fokker-Planck equations, which you can find as a useful introduction to the topics. So what we need to do now, from a practical point, if you take this kind of practitioner's approach to what is coming, and if you have in a way seen what are so the overarching motivation is to find a model for the transition probability. And this transition probability is a quantity which we don't have. So that means that we need to model it in a specific way, as we did in the Metropolis algorithm. So the overview here is given by the so-called Fokker-Planck equation. And you can now think, if you now look at the equation here, so you have now the equation 1 plus 1 dimension, x and time. So we have one spatial dimension and one temporal dimension. And the standard diffusion equation here, which leads to the Gaussian distribution or normal distribution, is the first term. But then we have a drift term here. And what you have here is the spatial derivative of the force. And this is a term which can be interpreted as a term, a so-called drift term. And the thing we are going to couple this with is an additional differential equation where we can now relate the derivative of x, which is the velocity of the system. So this follows from, actually what you have here is something which follows from Newton's law, but Newton's law where you have some random addition to the force, which takes into account fluctuations. Now, this equation here, if you use a standard Euler's method, you can actually find the new position. If you think of a discretized Euler methods for solving a differential equation, a first order differential equation, you can actually show that this can be written, since this has a stochastic term here, a random variable. This has as a solution the this constant d multiplied by this force term. So this is the force which is actually acting on the system. And then you have a delta t plus this term here. So this is normally called the Langevin equation. And we are going to discuss these things next week in a little bit more detail. So what we wanted to do now is more to look at the technical aspects which we need to think of. So in quantum mechanics, this quantity d is going to be equal to 1/2 times the h bar divided by the mass of the h bar squared divided by the mass. And we put h bar equal to 1 and the mass equal to 1. And there's going to be a parameter delta t, which we need to tune. And this delta t is going to correspond to the same stepping size which we had in the brute force algorithm. So we would need to tune this one. And in case we make it too large, we are going to jump in and out of the distribution. If we make it too small, we're going to stay in the same position for long, long times. Then, if we look at the equations, the so-called Fokker-Planck equation now, if we do this in more than one dimension, we would have a loop over the dimensions here. And then we have this equation here. And this equation, if you now look at the probability, we have an equation here when we now move over, when we have met the most likely state or the steady state, when we have reached the steady state, which means the equilibrium position, this equation should converge to the steady state or stationary probability, which means that the probability here is time independent. So the left-hand side is equal to 0. That means that we can study the requirements which we will have on this term f in order for the right-hand side to be 0. So what you see here is simply the right-hand side, which has been spelled out when we assume that the probability distribution is time independent. So we're assuming that when equilibrium has been reached, we are just jumping in and out of an equilibrium position. Now, as you see, there's a lot of assumptions which are being baked in the way we solve and set up the problem. So if you look at this term f, this can actually be rewritten. If you now look at the equations which we have here, it should have some dependence on x, and then there's a dp dx here, because we have a dp dx term here, and then we can assume that this term f must have this mathematical shape. If I plug that in, this specific mathematical shape, it means that this quantity has to be equal to what you see here. Now, the condition of a stationary density means that the left-hand side must again equal to 0, right? So this is this equation here, which we have rewritten out in terms of what you see here. And that means that what we need then, in order for this to be zero, there is an only one possible way by which we can find this function g, which you see here. And that means that this function g is now going to be given, since our probability is the wave function squared. That means that this object here, g, or this f, which we are plugged in, has to be given by the gradient of the wave function divided by the wave function times a factor of 2. And in Monte Carlo simulations, this term is actually called a quantum force. And you can think of this as a term which is responsible for pushing the walker towards regions of configuration space where the trial wave function is large, and that increases the efficiency of the simulation, in contrast to the standard metropolis algorithm, where the walker has the same probability of moving in every direction. So what we are doing now with this so-called drift term / quantum force is that we are adding a constraint on the way the random walker jumps in space. Now we can actually plug this in, and you can show then that you can get a so-called Green's functions, if you're familiar with the theory of Green's functions, where we now can calculate this transition probability. So the Green's function is nothing but a transition probability from x to y in a time step delta t, which is now given by these terms here. So we are not going to derive this in this course. You can find in the textbooks which I mentioned here, you can look up the derivations in the Van Kampen's textbook if you're interested. But we are just going to use these results. That's the basic philosophy here. And you can actually show that when you plug this into the Fokker-Planck equation, you can then find this distribution in the same way as we did for the standard diffusion equation. In the standard diffusion equation, this term with f of x disappears. And this means now that this equation is not reversible. So if I move from x to y, there will be a force here which depends on the position in y. So that means that when I take the ratio now, I actually need to take the ratios of these two transition probabilities. And now the ratio which we are going to look at is now going to be the Metropolis Hastings algorithm being implemented. And now we have a ratio here between these g's, or transition probabilities, which is different from 1. And then we have to multiply this with a trial wave function. So this is now the ratio which we're going to use in the Metropolis algorithm in order to accept or reject a specific move. So what we are going to need now, and we will continue these discussions next week as well, is actually to implement important sampling. So this is the next technicality which we need to think of. So if you look at the code here, this code is the same as the one we have been discussing previously, and it's slightly different from what you have in project 1, but it's not that different. So these are 2 electrons in 2 dimensions in a harmonic oscillator potential. So this is highly relevant for what you're doing. But instead of having the interactions between the bosons, which is set up in the project description, we are looking at the Coulomb interaction. So this is a system of so-called quantum dots. And for the 2 electron case in 2 dimensions, we can solve this problem analytically. It's actually one of the few problems, many-body problems, which can be solved analytically. And the energy, when we put the oscillator frequency to 1, and we put h bar equal to the mass, equal to the electric charge, equal to 1, then the energy for this specific system with these parameters is equal to 3.0. That's the result we should get for the energy. Now, so let's look closer at what we need. So I provide you with a Python code here. We are going to continue these discussions later as well. So the thing which we need to do now, in addition to having the trial wave function, which is listed here, this is also a case where we don't need, or where we haven't used, automatic differentiation. So I've actually calculated the second derivative analytically. And this is listed down here for the Coulomb case. So it's a kind of, it's an ugly equation. And I also have the so-called quantum force here, which is then also given by an analytical expression. And I'm coming back to these expressions when we meet again next week. The analytical expressions are derived down in the slides here. But what we need now is to add this so-called quantum force. And then when we now do the Monte Carlo sampling, we need now to define obviously the old positions and the new positions. I have this time step variable, which I put to 0.05. I have the seed for the random number generator. I'm looping over parameters, and since this is a harmonic oscillator, it has a minimum for the alpha value equal to 1. I now also have a slightly more complicated wave function than you guys have. So in the beginning, when you are setting up the code, you should do everything with a non-interacting case. And for the non-interacting case, whether you're doing 1, 2, or 3 dimensions for the harmonic oscillator, you have analytical expressions all the time for the energy, and you know exactly what you should get. Now, in this case, I have an additional variational parameter in the correlated part of the wave function. But so in this case, there are 2 variational parameters, and I'm seeking the minimum of that. So I set up an initial position, and now the initial position is given by a normal distribution with a standard deviation 1 and mean value 0. And this is multiplied by the square root of this time step. So this goes back to the Langevin equation. So instead of placing myself randomly, I'm now using this equation which we have here. And I define an initial position, which is now simply given by this normal distribution here times the square root of delta t. And then I add, in the next case, I add this term in order to find the next position. And that's where I need this so-called quantum force. So I need an expression for that. That's an element we have to code. So I calculate the old quantum force and the new one. And in the Monte Carlo sampling now, the new position, so I calculate first the old wave function in the old position, and the same with the quantum force. And now I have a new position, which you can see here, which is the old position plus this normal variable times the square time step, multiplied or added the quantum force times this time step times this constant d, which is just a half. And then I calculate the new wave function. I calculate with the new wave function, I can calculate the new quantum force. And then I have the Green's function, which is simply now calculated as the ratio between the Green's function, or this probability distribution from the previous time step with a new one. So what I'm doing now, I'm not calculating an exponential divided by an exponential, but I'm calculating the arguments to the exponential in the numerator and in the denominator. So this piece which you see here, this one is nothing but the argument to the function which you see up here. So I'm calculating this argument. And since I'm taking the ratio, I'm taking the arguments of the denominator and the numerator. And then I take the exponential afterwards, because it's stupid to calculate 2 exponentials and then divide. So I just calculate first the arguments and then take the exponential. And this is what is done here. So I calculate the arguments in here, the highlighted part, and then I calculate the Green's function, which is just the exponential of these arguments here. And here I perform my Metropolis Hastings algorithm. So if random number is less or equal to this probability ratio, which is the wave function nu squared, wave function old squared, times this Green's function. So the Green's function is now the one which represents my importance sampling. If I do that, then if this step is accepted, the new position is the updated position and the updated quantum force. I get the new wave function. I calculate the new local energy and then I update the averages which I need to compute here. So what you would see now for this specific case, where I look at two variational parameters, two particles in two dimensions, and then I have 10 variational parameters, 10 alpha values and 10 beta values, so 100 parameters. And then I perform the calculation here. You will see now that the result has a minimum around 1 for this alpha, and it has a minimum around a beta value, which is closer to 0.3. And I actually have results which are almost spot on the analytical result. Now, in the slides here, there's also a link to the same element, which is coded into the C++ code. And these are things which we will discuss in more detail during the lab sessions. So what I wanted to do today was more to give you the overarching view of what needs to be included in the code in order to avoid this kind of brute force Monte Carlo sampling. And with the brute force Monte Carlo sampling, you can easily get to the answers, but you have a less efficient algorithm when it comes to moving the random walkers in the space of all possible positions or configurations. So the elements which you would need, and I recommend when you're coding now that you can take this example. This example here contains the harmonic oscillator. So if you look at the wave function here, it has a wave function, this piece here, which is just the standard harmonic oscillator. And then it contains an additional piece which comes from correlations due to the Coulomb force. And you can neglect that. So the first part is the harmonic oscillator. That means that your local energy is just going to contain these two terms, these terms. The other terms which you see here follow from the derivatives of the kinetic energy for the two-particle correlation function. Then the quantum force is easy to set up for the harmonic oscillator, because it's just going to be given by this -2 times r times the parameter alpha. That's going to be your, you can forget the other parameters here, because they contain the derivatives of a function which depends on the interparticle distance. So the setting these quantities up for the non-interacting case for bosons is something which, one, we have analytical results for 1, 2, 3, hundreds of particles. We have analytical results for 1, 2, and 3 dimensions or higher dimensions. So it means that you know exactly what you should get. And that's an extremely valuable feature, because it allows us to benchmark the code we are developing while we keep adding all these ingredients. So if everything works fine with importance sampling for the non-interacting case, which is just a plain harmonic oscillator, then we know that if we don't get reasonable results with the interaction part, then we've done something wrong when it comes to implementing the interaction piece, because the rest of the machinery should be functioning correctly if you get the harmonic oscillator well in 1, 2, 3 dimensions and for many particles. So I would now, when you have implemented the basic brute force Monte Carlo code, what I would recommend you to do now is to start thinking of baking in these new elements. And you can look at this function which you have here, this simple Python code. So try to keep it as simple as possible and just try to implement that one without thinking of automatic differentiation, but just plugging in the analytical derivatives. Okay, I'm going to stop here, but we are going to repeat these things next week. And then we're also going to look a little bit more into the connection with the Fokker-Planck equation, and also on how to code these things in a more efficient way. So this stops today's lecture.